So, the streaming should be just started. Let me know if everything is okay, if you can hear me, if you can see the screen and the video. In the meanwhile, we will wait for a few minutes to see if someone comes, up to 11:05. And in the meanwhile, I'm taking the chat so that I can see your messages. And of course, you can tell me whether the streaming is actually going or not. Okay. Actually, I can't see. Okay, audio, the volume should be higher. Probably now it's better. Is it better now? I can also take a little bit the volume even up. Okay, probably I can also, no. From here it's already at the maximum level. I am only, okay. There should not be so much noise. Yes, so probably I can set it even louder, like this. And, okay, take the microphone closer to me. Now? Is it okay? Yeah. Ottimo, perfect. Well, then I guess we can start, because it's 11:05 as promised. I still cannot see the live on YouTube, but probably it's just a problem here. So if you can see me and hear me, then the professor will answer to your questions and tell me if there are any problems of any kind with the streaming. Okay? Okay, then I am starting. So today we will see an exercise of localization with the particle filters. The localization problem is the one that we have already seen in previous exercises. We want to determine the pose of the robot, which in this case moves on a 2D plane, to track the pose of the robot. For this, we have used different methods. We have used the extended Kalman, the unscented Kalman, and now today we will see particle filters. So, as usual, our robot Orazio moves on a 2D plane. Therefore, its pose is composed by the position in the 2D plane and its orientation. Orazio is controlled by translational and rotational velocities according to the unicycle model. It is able to, it comes with sensors that can provide the position of the landmarks in the robot frame. So it is able to sense a set of landmarks through these special 2D landmark sensors, which provide the robot with the relative position of the landmarks that it can see in a specific pose. Now, landmarks in this exercise are indistinguishable, so we will be performing data association. The location of the landmarks in the world is known. meaning that the robot has a table of correspondences between landmark identifier and landmark position in the world. Now, we will develop a particle filter-based algorithm to track the pose of Orazio as it moves. Again, the pose of Orazio is a pose in the 2D plane, and therefore we have 2D position, x and y coordinates, and the robot orientation. The inputs to our algorithm will be, as usual, the velocity inputs and the landmark measurements. The inputs are used for the prediction step, the measurements are used for the update step. The prior knowledge about the map in this case is represented by the location of the landmarks in the world. We are addressing a localization problem, not a mapping problem, so the map is given, and in this particular case, it is given by the set of locations of the landmarks in the world. Now, our prior is represented by a map, which is a set of landmark coordinates. Landmark coordinates are x and y position of the landmark in the world frame, and therefore they are vectors belonging to R2. The domains, as in previous exercises, the robot moves on a 2D plane, so its state is an element of the special Euclidean group of dimension 2, which is the set of homogeneous transformations consisting of a translation vector with a plane and an orientation which is given by the rotation matrix. Controls are vectors belonging to R2 because we have translational and rotational velocities, both belonging to the set of the real numbers. In this case, we are embedding the product times the time interval in order to have a compact expression of the Euler integration of the unicycle model. Now, measurements, as I was already mentioning, are positions of the landmarks in the robot frame, and therefore they are element of R2. The vectors consisting of two elements, both belonging to the set of real numbers. Now, we will use a Euclidean parametrization of all non-Euclidean spaces. In this case, while controls and observations belong to Euclidean spaces, the state of the robot belongs to a non-Euclidean space because we have a rotation matrix. And then, in order to have a Euclidean parametrization, what we do is we represent elements in SC2 as elements in R3, using the Euclidean parametrization, the easiest Euclidean parametrization. In this case, we have that the state of the robot is composed by x and y position and orientation, which is given by a number representing the angle of the orientation of the robot. Now, the transition function is the one that you have already seen from previous exercises. The transition function allows you to compute the pose of the robot at time t, given the pose at time t minus 1, and the control at time t minus 1. It is a nonlinear function because we have trigonometric functions cosinus and sinus. And it is the Euler integration of the unicycle model. Notice that UT1 and UT2 embed the product by the time interval, and this is why this simple expression is exactly the Euler integration of the unicycle model. Now, the measurement function, as usual, the measurement function allows you to predict the measurement given the current estimate of the robot pose. Assuming that the landmarks are distinguishable and that data association is given, then what we have is that the measurement corresponding to the ith landmark is given by this expression, where we use the inverse of the pose of the robot, of the current estimate of the pose of the robot, and the position of the ith landmark in the word frame in order to obtain the measurement, which is the position of the ith landmark in the robot frame. I won't comment further this formula, as it is the one that you already know from the previous exercises. Now, at each point in time, our robot senses a subset of landmarks, say k of them, and therefore the measurement consists of a stack of all these measurements. Now, so far, we have always considered the control noise as a Gaussian, because we were only modeling Gaussians. Also, in the case of unscented Kalman filter, we were considering Gaussian approximations of distributions. But in this case, as we are using a particle filter, then we can remove the Gaussian assumption and we can consider more general probability distributions. In this case, as an example, we assume that velocity inputs are affected by uniform noise between -0.5 and 5, whose amplitude grows with the speed. We have already mentioned in the previous lessons that the idea that noise depends on the speed, that the amplitude of the noise depends on the speed, is very reasonable. Because imagine that the two wheels are not perfectly equal, or that the terrain is not perfectly flat, then the speed will affect the amplitude of the noise resulting from these physical effects. Now, translational and rotational noise are assumed to be independent as in previous exercises, and therefore we have that the two components of the noise only depend on the relative component of the velocity. In the first component, we only have ut1, which is the linear velocity, and in the second, ut2, which is the angular velocity. Now, let us move to the measurement noise. The assumption is the same that you have already seen in previous exercises, meaning that the measurement noise is zero mean with constant covariance matrix. And with this noise, we have that the observation model, that is the probability of getting observations ETI given the pose of the robot, is a Gaussian, again, a Gaussian distribution, which has this formula here, where you can recognize that the difference between the prediction of the measurement and the measurement has zero mean, and that the covariance is constant, because it is the one that you have here. Now, under the assumption that measurements coming from different landmarks are independent given the pose of the robot, then the joint probability distribution over the measurements coming from different landmarks can be written as the product of the probability of getting the measurement from a specific landmark given the pose of the robot. This is an assumption that we will exploit again during the theory part of this course. So, once we are done with the measurement model and with the prediction model, we can move to the actual implementation of the particle filter, which is the most interesting part of this lesson. So, if there are any comments so far, I will take them. Otherwise, we will move to the particle filters implementation. Okay. I guess I can continue also because there was not much new concepts. So let us move to the predict function. And as I was mentioning, let us move to the particle filter implementation of the predict step. So when a new control becomes available, we can predict the pose of the robot at time t, given the information at time t minus 1. And this will be, in fact, a new distribution, a probability distribution. How do we obtain this probability distribution of the state at time t, given the information at time t minus 1? We obtain this by applying a transformation to the probability distribution of the state of the robot at time t minus 1 being given the information at time t minus 1. Now, this transformation is given by the transition function, which is nonlinear. In the extended Kalman filter, we were considering a linear approximation, and indeed we needed to compute the Jacobians, if you can remember. In the uncented Kalman implementation, instead, we were able to propagate the sigma points according to a nonlinear function. So, no need to compute Jacobians. Here again, in the particle filter case, we can directly apply the prediction function to the particles, and so there is no need to compute Jacobians, as in the unscented Kalman case. So, in this case, we focus on this formula and see that the distribution of the state at time t, given the information at time t minus 1, is described through the particles and the corresponding weights. Now, when we propagate a distribution through a function, which in this case is the function f, the weights of the particles stays the same, while only the positions of the particle change. And in this case, we can compute the particles of the state at time t given the state at time t minus 1 by applying the motion model to the particles of the state at time t minus 1 given the information at time t minus 1 and to the control. Now, what we do is we take the available control input, which is ut minus 1, and add particles generated from the control noise distribution, which is the one that we have seen here. Okay, so here we have defined that we have seen that velocity inputs are affected by a specific type of noise, which is a uniform noise. But the important thing is that we are able to compute a set of particles out of this distribution, whatever form it has. In this case, it is a uniform distribution. And we can apply these particles to the control ut minus 1. And by doing this, we are propagating the distribution xt minus 1 given t minus 1. Notice that if we were only to apply predict step and no update step, then the uncertainty would only increase, as we have already mentioned in previous exercises. So here you have an example of how the distribution evolves, the distribution of the state evolves in time when the robot moves on a square if there is no update, which reduces, of course, the uncertainty because you can exploit the knowledge of the measurement in order to know which particles are more likely. So,
I have a doubt about the connection between the particle filter and the unscented Gaussian. Because are they almost the same? Because we still have some sample points. If I understand correctly, the only difference is that in the unscented Gaussian, we take only a points and on specific paths, while in the particle filter we take a lot of random points. But I think that conceptually they're similar, right?
It is similar, but in the unscented Kalman filter, we are only thinking to a Gaussian, and also the way we take sigma points is affected. All the formulas that we have seen and the manipulations in order to obtain sigma points gives us a Gaussian approximation of the probability distribution. So the Gaussian approximation is always in the back of our mind and affects the way we take the points. While here we take the points completely randomly in order to be able to capture also distributions that are non-Gaussian at all, like uniform distributions, as you see in this example, or distributions that have more than one maximum, for example. This is another very interesting case in which you have multiple hypotheses that are important in the same way. And an example of this is the perceptual aliasing case, where you will have a set of particles in front of different doors which look similar due to perceptual aliasing. So what I want to stress is that particle filter is even more general than the unscented, because in the unscented case you are taking the points. When you take the sigma points, you are giving a Gaussian approximation of the distribution. So say you have a distribution, whatever it is, and then you take the sigma points, and when you take the sigma points, you are considering a Gaussian, in the sense that when you go from sigma points, you will always get a Gaussian. So I know probably it was it can be even clearer, but the idea is that particles are more powerful, because particles can represent whatever distribution. Okay, and so what they share though is that you do not need to compute Jacobians, because you can propagate sigma points and particles through nonlinear functions. However, if you remember, in the case of unscented, what we do is we propagate sigma points, but then get back to the Gaussian assumption, get back to the Gaussian distribution, while here we never get back to the Gaussian distribution. So particles are even more powerful than unscented Kalman. Okay, so now let us, thank you for the question. Let us move to the code. So you are given a prediction function to fill in, where it has as inputs a set of samples and the transition structure, from which you can retrieve the linear and the angular velocity as usual. Anyway, this is done for you. You don't have to remember. And and the output of this function is a new set of samples. The set of samples obtained using this formula here. There is no need to provide the weights as well, because weights do not change. So here you see that we are computing A1 and A2 according to a few slides before. And then what we do is, for all the particles, we want to apply the motion model. You have a file called the motion model, which you can use. So here what you will be doing is compute the new sample by applying the motion model to the current sample, and the control input summed up with with a particle from the distribution of the control noise. So in line 19, you will have exactly to write down this equation here, which is the application of the motion model to the samples of the state at time t-1 given the information at time t-1, and the control, which is ux, u theta, collected here for you, plus an instance of a particle from the distribution of the control noise. Okay, so this should be quite clear. Now, if this is clear, we can move to the update. Now, as I was mentioning in the second slide, in the very first slide, in this case, we assume that landmarks are not distinguishable. So we need to address the data association problem as well. We will do this in a greedy manner for each particle, meaning that what we do is this. According to the theory of particle filters, we need to modify the weight of each of the particles coming from the prediction step according to the likelihood of the particle. Each particle, xti, in particular this is xt given t-1i, each of the particles indeed has an associated likelihood. And in particular, zt is the measurement that we have, and of course we want that after the update step, particles that are more likely according to the measurement will have a higher weight, and particles that are less likely will have a lower weight. First of all, we need to compute the probability of this particular measurement, z of t, given the particle. We do this as follows. We construct a matrix of costs where each entry is the Malanobis distance of the nth measurement with the prediction of the measurement from the nth landmark. Here in the slides you only have one entry, LMNI. What you have to imagine, and what we will see in the code, is that we are assembling a matrix, a whole matrix, which is as high as the number of measurements, and it has as many columns as the number of landmarks. And what we do is we fill all the entries by applying this formula here, where you can recognize the covariance sigma z, which is constant, and the difference between the prediction of the measurement given the particle xi associated to the nth landmark and the nth measurement zm. Now, what we do in order to perform data association and to compute the likelihood of the particle, of the current particle xti, is we provide an association between measurement and landmark, and in particular what we do is we compute the minimum over the rows the minimum over the rows to take the likelihood of the measurement. So here the minimum over m of lmn I means taking for measurement m the landmark which provides the lowest cost. And this is like saying that we are associating the nth measurement with the with a landmark n. Now, what we do is we take as a likelihood the exponential function of the sum over m of all the likelihood coming from the measurements. And then what we do is we apply the heuristic so that if the value of the if the cost of the association is higher than a given threshold del miss, then we assume that we cannot associate the mth measurement with any of the landmarks, and therefore in the computation of the likelihood we will consider this as a miss and write L miss. So what we do is we collect how many miss we have in the variable k, and then we multiply L miss times this variable, which is the number of dropped measurements, for which we were not able to determine the landmark producing it. Okay. Remember that this formula comes directly from this formula here, where we were saying that measurements coming from the landmarks are independent given the state of the robot. And then the joint distribution becomes a product. So the product of Gaussians is the product of type e to the minus h minus z for all the measurements, and all these products becomes a summation in this formula here. So this summation comes directly from this expression here, where we were mentioning the independence of the measurements given the state of the robot. Okay, so under this assumption, it should be straightforward to obtain this formula.
Sorry.
Yes?
I get the summation where the assumption, but the k times L miss.
Okay.
That term in the previous formula, where it comes from?
Yes, okay, so this formula comes from the fact that we should have a cost for each cost, so say the Mahalanobis distance, a cost for each measurement. And so when we are able to determine the most favorable landmark, the most likely landmark to have produced that measurement, then we write LMI. When we are not able to do this, we could, in principle, use LMI again. We could write summation over all m of LMI, but then what we say is, okay, when it is greater than L miss, I just avoid doing this and admit that LMI is equal to L miss. It's the same formula. Also in the case, okay, so the question, sorry for those that are online, the question is, I get this summation, but I do not get this. The answer is that you could avoid this term, KL miss, and use all summations of LMI. But then, what we do is when LMI is bigger than L miss, we assume that LMI is equal to L miss. As saying, okay, this measurement, I'm not able to associate it with any of the landmarks. It is a dropped measurement, so LMI is equal to L miss. But if LMI is equal to L miss, then we can take all the terms with LMI equal to L miss off of this summation, and if there are ki of them, then we will have minus ki L miss minus summation over m of LMI. Okay, thank you for the question. Now, if this is clear, of course, I have to mention that this is a much easier implementation than the data association problem that we have seen with extended Kalman filter SLAM with unknown data association. In that case, we will taking care, we will using more heuristics in order to perform the data association, and we will considering the best friends and lonely best friends heuristics as well. In this case, we are only using a gating procedure, okay, because we are saying that if LMI is bigger than a given L miss, then we have a dropped measurement, which is like saying that we cannot associate measurement M with any of the with any of the landmarks, and this is corresponds to the gating procedure, but we are not considering neither the best friends nor the lonely best friends. So this is a simplified version of data association. It's just for the purpose of showing particle filter and let you focus on particle filters. Okay. So once we have mentioned this, if this makes sense to you, we can see the code, or perhaps, yes, the code. No more slides on this. And so this is in the slide, we see that this is a greedy manner, okay? It's, we say greedy because we are only taking the very first heuristic, which is the gating heuristic, and letting the best friends and only best friends away. Okay. So, if this makes sense, we can move on and see how this becomes code. So you have a function called update, which takes as input samples and weights corresponding to the distribution of the state at time t, given the information at time t minus 1. We have landmarks and observations. We have landmarks because we know the position of the landmarks in the word frame. We do not know which landmark we are observing, but for each landmark we know where it is in the word.
I have a question about each particle is sampling of the robot position, the robot angle, but also the current idea that have of the landmarks, right? It is sampling from the whole state, right?
In the state, we only have the robot pose in the state. Okay, this perhaps I can be clearer. So the question is, do we have, are the particles xi, which I am showing here, abstracted from a distribution which has as variables the states and the landmarks? So how do we abstract this? The question is that in general, in a SLAM problem, in a simultaneous localization and mapping problem, we have that particles indeed have the state of the robot and the position of the landmarks. But in this exercise, we are considering a localization problem. So the state is only consists of the state of the robot. It's 3 coordinates, the x, y, and theta of the robot, in this case, because it's a localization problem. Keep the two things, the data association and the mapping problem, distinct. Do not make confusion between data association and mapping, because I will try to explain. In this case, we have the map in the sense that we have a table, say, somewhere, which associates the idea of the landmark to the position of the landmark in the word. But when we take a measurement from the word, we do not know which landmark produces it. And this is why we are performing data association. But this does not mean that we have to put the landmark position in the state, because landmark position is known. It's just that we do not know which landmark produces a given measurement. The problem is simpler than you're thinking. Okay, so here, for example, we can use the knowledge, and you will see this also in the code, of where the landmark is. No problem with that. And we are not taking the knowledge of where the landmark is out of the state variables. We are taking this from the map. I will be clearer from the code. Okay, so move to the code. We are taking the landmarks. Now, here you see landmarks, but indeed it could be map. Why? Because here, inside the loop, what we do is we apply the measurement function to a particle and to a landmark. But as you can see, we are not taking this landmark x and the landmark y from the state vector. We are taking landmark x and landmark y from the structure landmark. I think I will explain this function and then go back on this, but I tried to be a little bit clearer, okay? Is it already clearer? Okay, perfect. So, now that we have further explained the difference between data association and mapping, meaning that we can have an instance of a localization problem where we know the map, but we do not have data association, we can move to the update function in particular. So what we do here is we have a threshold, an LMIS. We have a covariance matrix, which is constant. This covariance matrix is the one that you have here. Okay. And then what we do is we loop over the particles and again over the landmarks and the measurements. Why? So for each of the particles, what we do is we build a cost matrix, which we call LMN, that has as many rows as the number of landmarks seen, which means as many rows as the number of measurements in the end. And it has as many columns as the number of landmarks in the map. We take a particle out of the distribution, out of the set of all particles. And then what we do is we fill this matrix, LMN, the cost matrix, for this specific particle. So what we have to do is to fill each entry with this value here, or with LMIS, if it is a dropped measurement. So what we do is for all the landmarks, we apply the measurement function to the current particle and to the current landmark, which is observed, to obtain the current age. Current age corresponds to this function here. Okay? But as you can see here, we are using the knowledge of the map, because we are taking the position of the landmark, its x and y coordinate, from the structure landmark, which is one of the landmarks which is known from the beginning of the run. If we were dealing with a mapping problem, then here you won't have a landmark from the structure of landmarks, but you will have an element of the state variable, of the state vector. So once you have computed this age function, for each of the landmarks seen, you get the observation and you compute the entry of the cost matrix, which should be the Malanobis distance between the current age and the measurement. So here you will have to fill these two rows by writing that delta is the difference between the age and the measurement, and that LMN is the delta, it's the norm of delta weighted by the covariance matrix, which is exactly what you have here. Okay? Now at this point, what you do is you loop over the number of particles, you check if there are dropped measurements, which means that you check if the negative log likelihood is greater than the threshold LMIS. In this case, you say that this is a dropped measurement and increment the variable dropped measurement, and you set the negative log likelihood to 0, but this is just an implementation detail. What you have to focus on is that out of this for loop, you have you have in the sum of negative log likelihood this term here, the sum of all the negative log likelihood coming from measurements which you were able to associate with a landmark. And then in the weights variable here, you will have to multiply the weights at time t given the weights at time t minus 1, which is an input of the function update, times this expression where you have both the sum of the negative log likelihood and the dropped measurement times L miss. So here, out of this cycle here, you will have the number of dropped measurements, which is the number of measurements whose negative log likelihood is bigger than the L miss, meaning that we were not able to associate this. And so we can use this inside this formula here. Okay, so in line 17, again, you are supposed to write down this expression by taking advantage of the number of dropped measurements, which corresponds to Ki in this formula, L miss, which is given, and the sum of negative log likelihood, which again is given, computed in line 16.
Yes, the question may be similar to one of the colleagues. Is the point of this miss heuristic that we want to avoid having a really huge number in the exponent? Because maybe if we don't do this and miss, and we put everything inside the summation, then we have a huge loss inside the exponent, and maybe this gives a numerical problem.
Yes, we do that for this reason, because here you will have a very big number, which means that the sum of negative log likelihood has a lower importance, and we want to give importance to this term, otherwise we will have an exponential value which is too low, and then we have difficulties in the final association and in the propagation of the code. But you can try if you want to, but the reason is to give more importance to terms that do have a meaning. Because in the end, we want to focus to those that we were able to associate, that we were indeed able.
So, intuitively, we don't really care that a really huge error becomes a little bit smaller, because, but we care that the ones that we actually have a reasonable estimate about become better.
Yes.
Okay, thanks.
Okay. So, now, I hope that this part is clear. Okay, explaining the code is always challenging, because you have like line 11, negative log likelihood equal to 0, which is just an implementation detail in order to be able to compute the sum of negative log likelihood using the sum operator. But when you will write down the to-dos, you will find by yourself these implementation tricks. Okay. So clearly it is not that we're saying that when a measurement has a negative log likelihood bigger than a miss, then we will consider it as a 0. Clearly this is not the meaning, it's just that you have to add together with the sum of negative log likelihood also the product of the number of dropped measurements times L miss. Do not miss this in the to-do. Okay. So if everything so far makes sense, I can move on with the update, with the second part of the update, okay? At this point, you have that the weights, you were able to update the weights of the particles while their position do not changes. Therefore, at this point, we need to resample. As you have seen in yesterday's lesson about importance resampling, what we do at this point is we want to take more samples with a higher weight. and less samples that have a lower weight, and give to all samples the same weight. So what we do is we take a uniform sample out of the distribution of the weights, which is a discrete distribution, and then we use the output of the uniform sampling of the distribution of the weights as index of the particles of the state. As a result, we will take particles with higher weight more frequently than particles with a lower weight. So, after the resampling, you can assign to all the particles the same weight. And of course, this is straightforward to compute because the weight that we assign to the particles will be equal to 1 over the number of particles, the number of samples. Okay. This is, again, for giving greater importance to particles that have a higher weight, which means that they are more likely according to the measurements that we got. Okay? Now, if this is clear, it should be the same thing as yesterday in the theory. We can move to the implementation again. So, we are describing here two functions, and after these two slides, the explanation of the program ends. We are explaining the function uniform sample and the function resample. You will only have to fill resample, but let's start from the uniform sample. So, the uniform sample takes the weights and the number of desired samples, and it returns the indices obtained from the uniform sampling of the distribution of the weights. So what we do is we compute a normalizer for the weights because, as you might remember, these weights here, obtained by doing the product with the P of zt given xt given t minus 1, these weights do not correspond to a probability distribution. We need a normalizer. And if you cannot remember, I can take the slides of yesterday. Otherwise, it's okay. So, if you can remember, we had yesterday the proportional sign, and there was a normalizer, okay, which was equal to the sum over I of this expression, of course. So what we do is we compute this normalizer, then we compute the step as 1 over the number of desired samples, and then what we do is we start by taking a y0, a coordinate value, which is a sample between 0 and 1 over the number of desired samples, as in yesterday's example about uniform sampling of a discrete distribution. Then we take yi equal to y0, but we'll increment this value, and write down the cumulative distribution. What we want to do is to consider the cumulative distribution, and based on that, take the sampling. So what we do is this. I will take the slides of yesterday, if I manage to exit exactly. So, here, probabilistic slides, it's the 15. Okay, so here. Okay, a little bit bigger, perhaps. Okay. So this code here, uniform sample, is exactly the implementation of this procedure here. So what we do is we take y0 as a sample between 0 and 1, and then we take a series of steps over the y-axis, which in this case are represented by the variable yi, and we write the cumulative of the distribution of the weights. So what we do is for each weight index, which starts from 1 and goes from the to the dimension of the weights, we compute the cumulative distribution, so we get this value at the first step, and then while the cumulative is bigger than the current y-axis that we are considering, then we can take a step over and eventually write in the sample indices vector the current weight index. The result of this operation is that we will have, as you can see here in this figure, we will have that a given index appear more than once. While we are staying in this loop, we are continuing to write the same index in the sample indices vector. And by doing this, weights that have samples that have a higher weight will be taken more than once, because we have repeated values in the sampled indices vector. If you consider this code here and this figure, you will realize that we are actually implementing exactly this mechanism over here. As an example, consider the second sample here, y1 in the code. What you would stay in this while loop for 2 cycles, because you have that also for y2 the cumulative is bigger than y2, and then you will write twice the value 2 in the sampled indices vector. Okay? I know it is not so easy to get at the first glimpse, but it should make sense, okay?
So if I understand correctly, we have some particle estimations, and then we apply the predicted update to get other weights for these particles. What is the conceptual need for the resampling?
We use resampling because otherwise we would have a lot of particles with very low weight. The problem is that as you propagate the filter and let it go without resampling, then you will have, okay, the probability distribution in principle is correct, is represented correctly, but you will have lots of particles that are not representative. So you are losing computation and preciseness on particles that have no importance at some point in time. So the resampling allows you to focus your attention and also your computational resources and your machine precision on particles that do have importance for your distribution.
So intuitively, each particle has a chance to be kept by this resampling that is proportional to its weight?
Yes, yes.
Okay.
Yeah, the idea is perfectly that one. So each particle has a chance to be kept that is proportional to its weight. This is why we are doing this. This uniform resample means exactly that in the sampled indices you will have repeated indices corresponding to higher weights. As in the example here, the second index would be repeated twice, okay? While, for example, the third one is never taken. Okay. Now, this was a little bit complicated, so we do not ask you to fill this function here. We ask you to fill this other code, resample, where you are only asked to use these formulas. In particular, the resample function takes as input samples and weights, the one before resampling, and the dimension of the samples. And then what it does is it computes the new samples and the new weights. So what you do is you take the vector of indices using uniform sample, you compute the weights. Now the new weights are all the same, so they are all 1 over the number of samples, while the new samples are obtained from the previous samples, but we are taking them at the indices coming from the uniform sample. So here what I expect you to do is to write that new samples at I is equal to samples at indices at I, okay? Then you will think more on this, but the idea is that you need to use the indices coming from the uniform sample, as in the formula that you have here. Okay, so now I guess that we can move to the code. And okay, actually we have already presented the code. So in your folder you have a 16 particle localization with a main, which is this, and an exercise folder. In the exercise folder you find motion model, where you do not have to do anything, but you also have resample, update, and measurement function, which I mentioned in the presentation. Here, as usual, you have in the main simulation cycle, where for all transition you apply the prediction and the update. And then in the end you have the resampling here. So you do not have to fill anything in the main, but open it to realize the procedure. Okay. Now, when all the to-dos will be completed, you could finally run the pf localization.m. It is indeed a little bit slow. We have like 1,000 particles, and this is due to the implementation in Octave. If you implement this in CPP, it will be much better. Indeed, and the correction, when I will show the correction, I will also show an example of particle filter in action in a C++ application, and I can tell you that it is usable, okay? So if you wait, I will let this going on so that you can see how it evolves. Again, it takes a little bit of time, but we are implementing this in MATLAB and without taking particular care on efficiency, because it's just for didactic use. So for teaching. Now, I think I will leave the streaming go on and let you do the exercise. You have time, say 40 minutes, so that in the end I will show the correction of the exercise, the solution. Again, I will let the streaming go on, but hide myself perhaps, but if you have any questions, please post them and we will answer. here, and you should now be able to hear me. One important question was about this. LMI is the minimum over M of LMNI. Clearly there is a typo, and the typo is that we should have minimum over N of LMNI, because we are doing the minimum over the row, which means that the row stays fixed and the column varies, so it's the minimum over N. And then also the index here M makes sense. Okay, and this is one typo. Of course, what we are doing is we want to have a cost value for each of the measurement, so it is correct that this is an LM and that we have a value for each of the measurement, but what we do is we take the minimum over N of LMN, meaning that we find the landmark which is the most likely. Okay, this is the first thing from people at the class. And the second one is that we were talking about the other little circle that you see in the simulation. Now let me take it. Source octave 16 animation. You have a square representing the robot, which is the best particle, and then we have this little circle over here, which is the ground truth. And you can see this by the draw particles function, which you can find in the tools, in particular in the visualization folder. Okay. So, hello to the people online. Here we have almost solved the exercise, so we can proceed with the solution. I am also preparing an application, C++, where you can see a real case of a particle filter. Otherwise, we will leave you with the Octave implementation, which, as you might probably have already seen, it is slow, no? So, give me just a second to let this go, and then I will start with the solution. So you have a few minutes if you want. Okay. Okay. Okay, perfect. I have everything set up. So let us start with the solution, first of all. They tell me that the audio is probably not on. Okay, is this better now? Should be a little bit higher. Okay, perfect. Then, let us start with the solution. We will start with the prediction function, and let us take the slides here. So, we are addressing this problem here. As I was mentioning in the lesson, we need to propagate the particles of the state at time t-1 given the information at time t-1 through the nonlinear motion model function, where we apply to each particle of the state the control plus a particle from the control noise distribution. Weights remain unchanged. So the solution of this part, where we ask you to fill this line here, meaning that you are looping over the particles, you have taken a sample from the control distribution, and you are asked to compute the samples at time t given the information at time t-1. How you do this? You do this by applying the motion model to the samples in input to the prediction function, which are the samples at time t-1 given the information at time t-1, and to the control. In particular, the control that you apply to the motion model is given by the current control input u plus a sample from the control noise. As I mentioned here in class, random gives you a number between 0 and 1. So random minus 0.5 gives you a sample from a uniform distribution between minus 0.5 and plus 0.5. So that this exactly coincides with the extraction of a sample from the control noise distribution, which we have seen here in the slides. Okay, now I guess I can move on with with the update. Let us briefly recall the meaning of the update. What we do is we want to assign new weights to the particle depending on how likely they are. And we do this by computing a likelihood for each particle, remembering that the measurements are independent given the pose. And therefore, we have that the probability of ZT given XTI is given by the exponential of this summation here. I will correct the typo in this line, where we have that for each measurement we take a likelihood, which is the minimum over the landmarks of the Mahalanobis distance between the prediction of the measurement and the actual measurement. When the cost is above a given threshold, then we use LMIS. Okay, so now you were asked to fill these two lines. So what you have is you have a cycle for loop over the landmarks, then you predict the measurement associated to landmark n, and you have to compute the Mahalanobis distance between the measurement associated with landmark n and the nth measurement, which is accessed by this row here, by this line. So going to the solution, what you have to do is you have to compute the delta as the difference between the h, which is the prediction of the landmark m in the robot, of the position of the landmark m in the robot frame, where in particular we assume that the robot position is given by the current particle, okay? So we compute current h, and then what we do is we take the difference between this and the measurement m, the mth measurement. Again, the measurement is a data structure where you have to take in particular x pose and y pose. You have to extract x pose and y pose out of the measurement. At this point, you can compute the corresponding entry in the LMN cost matrix, where you have the Mahalanobis distance between the prediction of the measurement and the actual measurement, which is computed by delta transpose times omega z times delta. Indeed, the Mahalanobis distance is the distance weighted by the covariance matrix. The covariance matrix was already computed here. Okay. And so you only needed to do delta transpose times omega times delta. Okay, then you were also asked to fill the update of the weights. The sum of the negative log likelihood was given. So the only thing that you have to do is to multiply the weights by the likelihood of the particle. And the likelihood of the particle is the exponential of minus dropped measurement times LMIS minus the sum of the negative log likelihood. If you compare this with the slides, you see that we are writing exactly this expression over here. Okay. Now, if this convinces you, then we can move to resample. And let's take the slides, resample. So in the resample, as we were mentioning, we use the uniform sample function, which is given. So you were only asked to fill the resample function by using the output of the uniform sample function. In particular, what you have is that the particles now have all the same weights. So new weights is already computed and is 1 over the dimension of the samples, while new samples are obtained from the samples using the indices from the uniform sample. Namely, the code becomes this. As you see, you use the samples at the indices obtained from the uniform sample. Okay, I hope this is clear to all of you. By doing this operation in the indices vector, we will have duplicated the indices corresponding to higher weights again. Now, I want to briefly show you the C++ application where we are using, it's a navigation module indeed, in our code base. And, okay, so let me take this. As you can see, we have the particles here, which are represented by these arrows over here, where the robot is located. We have a localization module in this application, which provides the localization of the robot. We have a planning module, which provides a trajectory given the current pose of the robot and the navigation goal. And then we have a third module, which is a ROS node, which is able to track this path generated from the planner. So the main components of this application that you will see running are the localization module, which uses a particle filter so that you see that it can be used in reality, even though in the octave exercise it was probably very slow. And then we have a planning module, which provides the path to the goal, and a third module, which transmits the control inputs through ROS. It's a ROS node. So I can give a node, a goal, for example, here. And as you see, the localization module is working quite well. It is not so slow as you might think. Okay. There are also more details in this application, especially in the planning and motion part. But it was just to show you a C++ particle filter in action. Okay, so said, it's 1 o'clock. So if we are all satisfied with the solution, I will close here the lecture, and I will push the solution and probably also refactor the folder and correct the typos, because indeed you were only asked to fill 3 files, update, resample, and prediction, while you have lots of other files in the exercise which should be outside. Okay? So I will do this and update the directory. Okay, so thank you. And I'm closing the streaming and say bye.